get out? Well, it certainly looks random. It's not random. It's been processed by our design. But what we need is a checker. Now, a checker is not a part of this lecture. Checker is hard work, but it's something that the verification team has to put together to say, given a certain set of inputs, and it may be a sequence of inputs, what is the output supposed to look like? If it catches a mismatch between its expectations and what the chip's actually doing, that's when you get a little error message and it's time to go do a little bug hunting and fixing it. Now, at the end of the day, if you just do this approach that we've shown here, you'll get fairly decent results. But did you actually cover all of the design that you were intending to cover? If you want to know that, then you have to add something called functional coverage to your design, which is monitors that look inside the design under test and observe the features that you believe that need to be exercised in order for you to have a device that's worth shipping, something that's functional. And a functional coverage gives you these little fill in the dot kind of things here, where red maybe indicates successfully tested or stimulated that part of the design, and white maybe means there's a hole in the design. Or it could be the other way around. You know, your random stimulus could be really good or really bad, but it never covers 100% as a general rule. And so then what are we going to do? We look at the functional coverage results, and you end up writing more tests. And by saying more tests, what we actually do is we come back and we run a second sweep at random numbers, but we change the constraints to force the design based on our knowledge of how the inputs affect the holes in our design, to try and force those to get stimulated. And we're hoping to increase the coverage there. By the way, when you increase the coverage on the things that are uncovered, it might be that you uncover some of the ones that you already had covered, but you keep the original test, so you got yourself 100% coverage at the end of the day if you work at it diligently. Well, let's take a look at some of the mechanisms that SystemVerilog provides for us for doing randomization. And first thing I want to make an observation is that Verilog for a long time has had some randomization in it. They've got a number of different functionalities in there, but $random is the most basic thing. It provides 32-bit numbers they're signed 32-bit numbers, but they're basically evenly distributed across the range of what a 32-bit number can represent, plus or minus 2 billion. All right, and the language standard specifies the exact algorithm so that all the simulators use the same random algorithm. However, the standard doesn't lack, they didn't think about this, something called random stability in $random. So SystemVerilog introduced something called $U random, rather than redefine something that already had it worked to a certain extent, but not in the sense that we need. And so $U random is simply an unsigned version of $random, but the algorithm's not specified. Instead, they require the issue of random stability to be handled. And by that, what I mean is every process in a simulation has to have an independent random number generator from every other process, and it's also true of any object. We'll talk about that in a few slides ahead a bit more. They also introduced something called U random range, where maybe you want to have the numbers between 2 and 11. There's some range of numbers that you want to produce, random numbers. And although I think I've seen a lot of code where people take $random, or in C you'll see rand, and they do a modulus on it, the problem is that what we want is evenly distributed random numbers. We want them to be, statistically evenly distributed across the whole range that's provided. And you cannot do that by just doing a modulus on a number. You'll end up with more things distributed towards one end or the other. And we're not going to go into that, but that is the case. And we've had other webinars on this topic in the past. Well, I was going to go on to talk about standard randomized, but before I do that, I want to show you this code that we're just showing here. I want to show you EDA Playground. This is the one time I'm going to jump in to EDA Playground. And what I want to show you is what we have in terms of a facility to explore the code. So every one of the slides that I have code on today, I will have a playground set up with that code and some other code supporting it, because we show code fragments in quite a few cases. and it's a complete simulation. And what I'll do, you'll see here in the left pane here, that's the actual SystemVerilog code. On the right over here is a comment around the output from running the simulation. Now, when you bring these up, you'll get a title as to what the thing is about. But when you want to run a simulation, EDA Playground allows you to choose a simulator. Of course, you'll choose the Siemens EDA. The Mentor Questa is the Siemens simulator. We're using the version 2021.3, a fairly recent version of the simulator here. You can set up compile time options and runtime options, and then you simply, after you put your code in here, all you do is you click on the Run button up here at the top, and it will run a simulation and produce some results. And then I copy-pasted those conveniently in the upper right pane, because in what we're using this for, I'm not using this design.sv file at all, so I just put a comment in there to capture the output. So you can run it yourself, or you can just observe the output, but I would encourage you to actually experiment with it. By the way, in order to get onto EDA Playground, you need to register with your company's email address, get an account, sign up, you'll have a profile, and if you do that and combine that with the links we send you later, and you'll be off and running to checking everything out and having a great time with that, hopefully. And hopefully there'll be some good learning to be found there. So getting back to random numbers in SystemVerilog, let's explore another function that was introduced, and this is probably the most important one that was introduced in the SystemVerilog. Is called it's in what's called a standard package called STD. It's called randomize, and this function it takes as arguments any number of variables. And so here I'm randomizing A, B, and C. And what it does is each of these has a certain range of values possible here, right? So we've got 8 bits on C, and we've got one bit each for A and B. No, I'm sorry, 8 bits each for A and B. So we've got 24 total bits. The idea of standard randomize is it randomizes the 3 variables all together as almost like a 24-bit number, if you will, and then assigns the numbers to them. So it's an even distribution of randomization across the variables that are in the argument. And again, this function has to exhibit the random stability issue that was brought up here, and it does. It has an interesting extra, some more syntax to it. We're going to see quite a bit of it a little bit later. It has the idea of having what are called constraints. Now, this is an example of what are called inline constraints down here at the lower right. And what I'm saying is I want you to randomize A, B, and C, but I want you to make sure that every time you produce them, that A is less than B and B is less than C. So I'm constraining the randomization a little bit and saying not all possible values are allowed here. I'm not just wide open. I'm constraining the results to something that I want. Now, it is possible because what happens to happen in order for this to happen, our EDA vendors, when they implement constrained random, they don't just choose random numbers and then say, oh, does it work? No, it doesn't. Let me try another random number. What they want to do is they actually do some equation solving, and they use what's called a constraint solver to come up with an equation so that they generate a random number. It just fits immediately and they get a result. But it's possible for this constraints to fail from time to time. It will fail, for example, if you state something that's completely impossible. I'll give you an example. A is less than B and B is less than A. That would not be a reasonable thing to ask. You can't have there's no two numbers that would have that property. Okay. So these constraint solvers sometimes can get rather complex. The constraints can be. And as a result, standard randomize actually returns a single bit value. We ignored it up here in this first line, but here we're capturing it, and it'll be a 0 or 1 to indicate success or failure. Okay, with that basic out there, let's take a little bit closer look at more of the kinds of things we can do with constraints. We're just going to visit this briefly, and then we'll move on to the next set of topics. So here's a standard randomize. Here we're saying that in that A, B, and C, that B must be inside, and then apparently A needs, it's not really saying it, but there's a range between A and C, all the numbers between A and C, and the value 0. Or A in the second randomization of A itself says A has to be either 0, 1, 2, 3, 4, 5, 6, 7 or 1247 to 247 to 255, and those are the only legal values. And it has to be evenly randomized across that set of values that we provide there. A little more complex version of it, here I'm running A, I'm saying I want the values 0 through 3 to occur with a weight of 1, but 4 through 7 each will have a weight of 8. And that means that it is 8 times more probable that I'll get a value between 4 to 7 than I will a value of 0 to 3 in terms of the output. In other words, I'm changing the weighting from a uniform distribution to something I explicitly control. The last one here is interesting. The little slash that you see in here, it says that each of the values 10 through 13 gets a weight distributed over a weight of 8, the weight compared to it. So if you imagine, you can get the value 4 8 times more probable than the value of A, but the value, you could also get a value 10, 11, 12, or 13. And if you want to think of it this way, it's not quite the same, but it's sort of like 10 gets a weight of 2 and so forth, because there's 4 values there. Each of them has a weight, effective weight of 2. And you can see those numbers down here. All right. So you can see there's several things. So there's more to the syntax. We'll look at some more of those towards the end of this lecture. All right, let's move now from the top 2 topics. We just discussed the verification methodology and some simple randomization. Let's talk about this idea of stability and control, because this is pretty important. And then I'm going to follow that by some some syntaxes that are rather useful in building up random. So random stability and seed. So it turns out that in SystemVerilog, we have processes. What's a process? It's an always block or an initial block. It's something that runs in parallel concurrently with another thing. And in hardware, we think of logic gates and things like that having this idea of concurrency. And so the idea of random stability is that when you start up the simulation, every process and every object, we'll get more to the objects a little bit later, has its own random number generator seeded such that it runs independent of the other processes. And the idea is that a random number in one process should not affect a random number in another process, the generation of random numbers in another process. And this will allow us, if we do a bug fix that might actually change the way random numbers are treated inside a particular process, that it doesn't affect what's going on in the other processes in the system. We need to have the system stable so that if we fix a bug, we want to see the same sequence of random numbers to try and reproduce the bug, but if we fixed it, see that it is fixed and it doesn't actually show up as a bug anymore. So, for example, in what we have here, we've got this process P1 and P2. There's no interaction between the two of them in terms of random numbers. As you generate additional random numbers, they run independently. So then we also have P3 and P4, which are inside a fork join, and they also run with no interaction. There should be a join statement here, ... We leave out a number of bits of code, as you'll see going through this whole thing. Now, there is, however, some built into this slide intentionally a dependency between some of them. So what we're going to see here is that P2 actually affects P3 and P4. And why is that? So P2 is where the fork join is embedded inside. So it's going to launch these processes start up after P2 started, and P2 is sitting here running some number of iterations of the random numbers. So the seeds that are used to start up P3 and P4 are actually generated when the processes are created. And therefore, change in code inside up here before we get to the fork will affect the random numbers generated down below. And that's an example of not having good random stability. So even though your simulator, in the case SystemVerilog specifically, specifies random stability, you can impose some instability in your design if you're not careful. Methodologies such as the UVM, the Universal Verification Methodology, take great pains to try to ensure that this does not happen. But it is something that every coder needs to be somewhat sensitive to and aware of. Now, where do these seeds come from? Well, they come from the startup. Let's move to the next slide here. The way seeds are done is that when you start up the simulation, there's an initial seed that you can actually control from the command line normally. It's very tool specific as to how you would do that. But you can set an initial seed, and then that seed is then used to generate the seeds for all the other processes. You basically generate a random number to use as a seed for each process. Well, we can in SystemVerilog grab hold of the process context through these couple of lines here, grab the process, and we can actually then set the seed for a given process. So we can be very specific in a given process to set its current random number generator seed. And in objects, we have also ability to do a similar kind of a thing here. But there's also another way to get, so we can also get the current, if you will, random status or state by calling this get rand state. And then this actually turns out to be a string, a string of characters. It varies from one vendor to another what it exactly contains, but it's essentially a set of random characters, if you will, from our perspective. And we could write that out to a file. And the reason we could write that out to a file is we might then later want to read it from that file, and we can call set random state and set it to a state. Now, this example here, we're grabbing the state, doing 4 random numbers, and then we set the state back to its original value that we got earlier and run it again, and you should see the same results before and after. And if you'll move to EDA Playground, you'll see that. Is the case. Now, this slide's entitled Resist Chaos. It's kind of a fun title here. It's a comment about random inputs to chips. We do not want totally random inputs on our designs. We need to intelligently choose values. For example, creating transactions where we just randomize an address, a data, and then whether or not we're going to do a read or a write operation with random is not very realistic stimulus. It's more likely that we would like to do something like we see at the bottom here, where we might randomize and decide, are we going to do a read or a write? And if we're going to do a read, well, then we only need to randomize the address. And if if we're going to do a write, we need to randomize the data as well as the address. So we have both of those things to consider here. So the address got randomized in both cases, so it actually occurred when we chose the cycle kind. So the point is, we do have to think a little bit before you choose, how you're going to generate your random numbers. A single constraint might not do exactly what you need. You may need to do it in several steps. As another interesting aid to this, there are several structures within SystemVerilog that allow us to choose randomly what to do. This is a case statement. Rand case is a case statement that randomly chooses one of the groups to execute here. Now, the number in front of the colon, in a case statement, we usually provide some kind of a value up here or an expression. Actually, we'll see that in just a second. These effectively are weights. In other words, the second one's 5 times more likely than the first one. Well, the idea here is you add these all up. They conveniently add up to 100 here. So you can think of these as percentages, but that's not a requirement of the tool. They're just weights. So add them all up, and then it's 1 out of whatever the total number. So 1 out of 100, 1%, 5%. This is the probability that the given line will execute. And that given line, by the way, can be a begin-end with a whole lot of code behind it, a subroutine calls and all types of things here. This is a very simple example. All right. We can do more with rand case. Those numbers don't have to be fixed. They can also be variable, as in equations. So, for example, here we might have ourselves inside a little loop, and we might compute the values of start or stop, and then set starts, give them default values, and then based on whether or not start or stop is active or not active. So if it's active, we do nothing. If it's not active, we do one of these others with the respective probabilities. So we can put an expression. The point is you can put an expression in that case and come up with some interesting code to stimulate your design. And so I've just highlighted there the code that does that. All right. Rand sequence is another construct that's kind of useful. Now this is I like to think of this almost like a state machine where we specify a starting, what they call a production. They're using grammar rules from programming languages oftentimes used here. So we're going to start at start. That makes good sense. Doesn't have to be starts, whatever name you give it. And at start, we're going to do part 1, followed by part 2, followed by part 3. And so part 1 displays, part 2 displays, part 3 repeats 100 times another production called repeated, which then chooses randomly between one of 3 possibilities here. And then it can display things. So maybe the output is what we see over here on the left. It can Rand sequence, just as with the Rand case, has some more extensions here. For example, here we have a production that has an if-else clause in it. So it chooses whether to call a production call action. Now, you'll notice this action contains arguments. So it turns out that actions actually can contain arguments to choose it. So you can get quite complex with this. I think that's enough to give you a sense of what's going on here. One last thing up here. Remember how we assigned weights in the distribution of our constraints earlier? Well, you can weight the probability of the different productions occurring up here on the first line. So that's a quick introduction to some simple randomization and constraint ideas here. We've also talked about stability control and then Rand sequence and Rand case. So now what we're going to do is we're going to move to more constraints, and then we're going to wrap up this talk with that. And then you can put your questions in the chat box if you have any concerning this particular presentation. All right. So the first thing I want to talk about is randomizing objects. So this is where your object-oriented stuff comes in. This is the only slide that gives you a hint at what an object is all about. So I'm sure most of us are familiar with C and the idea of a struct. And here I have a struct which has a direction, an address, and data as members. And using standard randomize, we could just randomize each of those 3 elements separately. The notion of object-oriented programming is to find something called a class, and part of what you have in a class is actually data fields, just like in a struct. So down here we have direction, address, and data, but we've added a keyword at the front. Inside a class in SystemVerilog, if you designate the data as RAND, what you're saying is this is a randomizable field of the class. And then when we do randomize, we simply say object dot and then say randomize, and it basically randomizes everything that was noted as rand inside the class or of the object. By the way, to get an object, you also had to say new on it. When you declare an object, typically you'll also assign it a value with a value new. And I'm not going to go into all of that. This is, again, you should know a little bit of object-oriented programming. You should get the sense of what's going on here. Well, if we've now randomized we can randomize the class. There's something else we can do, which is it turns out we can put constraints directly into the class itself. So here I have a constraint. Constraints have names. So this one's called ROM area. And this one has a constraint that says when you randomize these 3 fields here, we want the direction to be equal to read, and we want the address to be less than 7 FFFF. There's some points on here about where semicolons should occur and so forth in the language. One thing about SystemVerilog is kind of inconsistent on where semicolons are supposed to appear or not appear, so be careful with that. Anyway, back to what's going on here. So if we do that, what we end up with is we end up making all of our random number choices in this little area here. If we think about read versus write and the address ranges here, Turns out that's not very realistic for what we're trying to accomplish. What we're trying to accomplish here is kind of like a memory map. And we want to say that when we're doing a read, well, it turns out that the read-only memory is down here. But the distribution, it's not doing the job. So there's a little bit more syntax here. So take that constraint thing here, modify it a little bit, and say, look, if the address is less than that value, then the direction should be a read. When we do that, then we get distribution to say, okay, you can do read and write up here, because this is not the read-only memory, but read-only down here. And this is a way to express that using this implication operator in SystemVerilog constraints. Well, constraints have some more power. When we're using object-oriented notions here, what we can do is separate the data declaration into one class and then take that constraint out of it. And rather than modifying the original, don't do that, extend it. That is to say, create a new class. So here I have this memory map transaction, extending the bus transaction. So what it simply means is take everything in that bus transaction, throw it in here, and then we're going to add a constraint. So now we're adding the constraint to say where the read-only memory is, for example. And so it's quite a simple notion here. You can get a little bit fancier than that. You can then add some variables to the class. So here's my memory map transaction class, same as on the previous slide. But now what I've done, I've added a new variable called area. And the area can take on one of three values, RAM, ROM, or IO. And then I have a constraint, an address map. And I say, look, if it's read-only memory, then it's got to be in this address range, a little different way of expressing it. If it's in read-write RAM, it's here. And if it's in IO, it's got a different constraint. And you don't have to have just one constraint. You can have more. So constraints kind of add up. They're an AND operation here. So in this mem, I'm saying, look, if it's read-only, then the direction should be read. If it's IO, which is byte wide, then the upper bits should be set to 0. And then I want to set how often, because when you randomize, you're randomizing not only address, direction, and data, but also this area variable we introduced here. And so I'm saying, okay, the probability of read-only memory is 1, the weight is 1, 2, and 97. So lots of IO, very little RAM or ROM for this particular example. Okay, so classes and this idea of object-oriented constraints is a very powerful idea. But sometimes we actually want to combine that with this idea of what are called inline constraints. We've already seen this before. So here I have a very simple thing, right? Literally thing. Okay, you can randomize it. It randomizes all the variables. But maybe I don't want to create a new class at this point. Maybe I just want to do a very simple modification on it. So what I can do here is I can say randomize with, and then do the inline constraint on the class. Now, I could have a mixture of these. I can also have constraints inside the thing and use the with, in which case they combine to be a more severe constraint on here. So I can say randomize the address bit 0. Here's another one, and I've got a couple of different things going on inside here. We can also override constraints. So in this class thing here, I've got a couple of constraints, one called address even and address bit 4 to be 0, and they do respectively what they're supposed to do. And then I can extend my thing to have an odd address class where I say constraint. Now here's the interesting part. This says address even. That's just the name of the constraint from the base class that I'm extending. And because of that, this address even is going to override. It's going to replace this address. This one doesn't appear anymore, and they use a different constraint here. So whereas it was even before, now I'm going to make it odd. I change the 0 to a 1 and make it an odd constraint. In the same manner, I could change and have an even thing that extends thing and change the other constraint. Or I can override two constraints. Lots of different possibilities here. Another thing we can do is we can actually turn off randomization for an entire object. So if you imagine that I have an object where I said new before, so a class, a thing, and I can say randomization mode is 0 or off. And I can also turn it back on, by the way, for the entire object. And then I can come into it and say, well, actually the data field, and I want to randomize that, so I can turn on randomization for a specific data field, and then I can randomize it, and I'll just get the things that I turned on. I can turn on more than one thing with just multiple statements here, or turn some off. And I can change my mind. I can check to see whether or not it's on or off. I can be specific on that field. Is that one being randomized or not? Things like that. Now that's randomization for the entire object. We can also affect the constraints. We have a similar set of calls here. We have a constraint mode. We can turn off all the constraints. So constraints are on by default. We can turn them all off, and then we can turn on a particular one and randomize. And we can test to see whether or not the mode is on. By the way, the last piece where you're testing to see whether or not it's on, you'll notice that there's an empty, no argument. There's no value in the argument here. Whereas you put a 1 or a 0 to turn on or off in the other parts, because it's the same function name, constraint mode or constraint mode. Okay. Other nice things that we can do with constraints, we can do ordering here. So imagine I create this class C here, and it has 9 bits of data. It has a single bit and an 8-bit data field in here. And so if we simply randomize this class C, you get 9 bits, or one out of 512 possibilities here. Evenly distributed randomization is what you're going to get. However, we can extend C to get D, and we can say, look, when A is 0, I want B to be 0. And if we take a look at what that results in, you'll end up, it turns out that all these values are going to be forced to be 0 here, but it turns out all I really cared about was this first one. And I actually was thinking that the rest of these would have a similar probability. I was actually thinking when I did this that I would get 50% of my things to be, when A is equal to 0, I want it to force B to 0, and all the other possibilities in here, 50% of the of this total, which was out of 512. What I really wanted was, it's in the last column here. 1/2 of the time I get the first entry. I don't care about these. They're never going to show up. And then the other half of the time, it's evenly split, 1 out of 512 here. If I want to do that, the way I have to do it is because constraints, they are calculated. Remember, we talked about constraint solvers earlier. They're calculated with even distribution across the elements that exist. So over here, we only had 200. We had 256 at the bottom plus 1, 257. That's why we got that kind of a distribution. What we need to do is actually, on different syntax, we need to say, look, I want you to solve A before you go and solve B. And by doing that, we'll end up forcing the distribution to be what we want in E. So rather than having having it all glommed down here in the wrong distribution, but you got to be careful. It's one of these things where when you do these distributions, you have to think about what exactly you're specifying in terms of that end result. It's not always intuitive. Another thing we can do with constraints is we can actually call functions here. So here I have a function where I have data and a parity bit, and I have a little function that calculates parity. And what I can do with the constraint is I can say, well, the parity bit has a constraint called, parity has a constraint called parity bit, where I basically force the parity to be equal to the calculation for the parity. Now, if you will, that's forcing that value to be a value here. There's other ways we could have done this, by the way. Another way we could have done this is we could have turned off randomization on parity and simply jammed a value into it at the end. And we'll talk a little bit about that in just a second here. You can also, say you want to generate values and maybe have errors and things like that and not have parity. You can also, of course, turn off the constraints if you want to do that. Now, I want you to think a little bit about what we just did here. This function call, this can be a relatively complex function. It doesn't have to be as simple as what we see here. It can have for loops and other kinds of things. All of that plays into the constraint solver inputs that the EDA vendors have to deal with or whatever. And this is where a lot of people get into trouble. If you put in an arbitrarily complex function up here, oftentimes the constraint solvers have a real difficult time with it, and they can fail because of what's going on there. And interestingly enough, sometimes what will work with one simulation vendor won't work with another because they actually have independently designed their constraint solvers, and each vendor's claim to fame is their constraint solver. And there is no best one in my mind. That is to say, I know there are cases that one EDA vendor can solve that another one cannot, and vice versa. So it'd be nice if you could point to somebody and say they solve all the problems, but I dare say none of the EDA vendors would ever claim that. They might claim they're better, but might not be that they can solve all possible problems here. All right, how about arrays? Arrays are very useful things. Dynamic arrays in SystemVerilog are a very useful thing here. So what I've got here is this array, which I didn't specify how big it is. And I didn't specify how big it is because I'm going to have a constraint, and this constraint is going to cause the array to spring into existence, and so I have a length variable here. And my constraint says that the array size has to be equal to the length, and the length is going to be one of this choice of things with this constraint up here. So I choose my length in the constraint, and then that implicitly forces the array size, and the array springs into action. Now, that's interesting. I just set the array size, but I didn't set something else up, which is the contents of the array, which also you probably want to have randomized. So let's talk about constraining an array of objects. And I'm going to specify objects. Objects have some interesting things that we have to consider here. So here I have this object class inside of C. And so I have an array of objects, and they're randomized. I want to randomize the contents thereof, and I still have a length. So it turns out there's a couple of methods, one called pre and one called post. We're going to use post for this example. And what we're going to say is, look, we're going to constrain the array size like we did on the previous slide. And then after we're done randomizing, but before we return from randomize, we're going to do a little for loop here, and then we're going to go ahead and randomize each of the objects independently. So that's one way to approach it. By the way, don't forget, when you create an array of objects, you're actually getting an array of null references. You have to call new for each. You have to populate the contents of that array with a new object, and then you can randomize it. Now, I could have taken a slightly different approach. This one's actually not an array of objects per se, because we still have to do a populate, but say I just have an array of random numbers, in this case bytes. What I can do is I can set up the array during the before I'd start doing randomization. I could use uRandomRange to say, oh, set the length between 0 and 7, or maybe it's 1 to 7 if you want to make sure you never have an empty array. And then set up the length. And now when we do randomization, we can do randomization, and you can have a for each in here. So I'm going to go over each element and do randomization. Now, this is quite powerful. It also results in a rather large amount of work for the constraint solver, because it's going to simultaneously try to assign the random numbers to all of the elements of the array, so you get even distribution of randomization across the entire array. Now, these aren't very big arrays, so that's pretty good, but if you make the array large, you can imagine it could be a real trouble for a vendor's software to do that. A lot of memory and work to get that to work. We can also address constraints hierarchically. So, for example, here I have a coordinate class, and inside this vector, I have a coordinate inside it. And so what I can do is I can do things like inside the vector class, I can have a constraint that says that the local pos coordinate is got to be equal to this equation right here. So I'm referring to the coordinate within the class. I can also then randomize this thing that I just did with an additional inline constraint and say, look, coord.x. So I can dive down into the class, and there are a number of things we can do there. So you can have an arbitrarily complex class containing classes, objects. They're built up by composition, and then you can still constrain everything all the way down the chain. I got another really cool feature. Occasionally, we want all of the numbers that are chosen here to be different from one another, as in unique. And so one of the constraint syntaxes is say, I want unique A, B, and C. And you get what you expect here. We're just doing a straightforward randomization to get the numbers that we got out of here. One last topic I need to talk about. You remember we talked about the idea that randomize can possibly fail. Sometimes when it fails, it might be that you don't want that to be a hard stop for the simulation, an error. And in fact, everything we've discussed prior to this slide has actually been a hard fail if it fails, because if you're doing randomization, it's important to get the value. But in 2012, they introduced the notion of soft constraints. So if you annotate your constraint with the word soft, what it simply means is if it fails to randomize it, then that's okay. And it's not going to complain, no warning message, anything. It's just going to be allowed to do it. So here we have actually one where we're actually forcing failure. So class C says V's got to be equal to 1. So choose a random number, any number, as long as it's 1. Now, that's what I call, if you will, extreme random constraint, right? It's not an unusual constraint, it turns out. It's kind of a useful constraint to use for certain situations. And I'm not going to go right into that right now, but just to say here, it's got to be 1, but then extend the class C and say, no, it's got to be 2. Well, if this wasn't soft, you couldn't go anywhere. So this one's also soft because then class D contains an element of the extended class, and I'm saying that it needs to have the V has to have a value of 3. So 1, 2, 3. And then finally, when I actually used it, I went to randomize it. I added an additional constraint on the outside. I said, no, I want it to be 4. Okay, so you might think that's amusing. No, the reason for putting this setup here is that there's an increasing priority here. Which one wins is the question. And so it turns out that there is a set of priorities here that if the second one takes priority, so inheriting has more importance than what's in the base class, so the descendants get to choose, if you will, who wins. If you have an instantiated constraint member here, this one would win. And then finally, if you have inline constraints, the inline would win in that case. So there is a well-defined priority on that. Okay, so this has been just like bam, 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 a really rapid visitation of SystemVerilog randomization. But that was intentional. A few things just in summary here. The verification strategy requires us to generate data, and we're going to use what we call constrained random. But we also need a method for measurement. We need functional verification coverage. We also need checking of data. That goes without saying. You got to make sure your design works. But that's something that we learned on the very front end of this slide. And the second thing we learned is there are a whole lot of different randomization features in SystemVerilog. I would say that standard randomize is probably, with constraints, is probably the most important concept we encountered. But you should not ignore $urandom and urandom range. Those are certainly useful. I would avoid $random in most cases because it doesn't have the random stability that we need for our designs here. And we also talked about the idea of base classes that were extended with constraints and a lot of different approaches for configuration and control. Well, having said all the things that we said in this presentation, you've learned quite a lot about randomization, but what we have not talked about is functional coverage. And I just want to point this out because some people think, well, now I know how to randomize things. I'll put my constrained random in there. But how do you know if you actually tested the design? Well, that's not part of this lecture. So sorry, that would take another hour to go through that at a minimum to deal with that. So the topic functional coverage is something that you need to learn if you're going to do constrained random. In fact, I would almost say you should learn coverage before you learn constrained random, but now at least you have the motivation for why you want to learn functional coverage to make your design work. In fact, Doulos offers a number of courses. So one of the things I want to just encourage you to think about, if this presentation was for newcomers to this whole thing here, we have courses on SystemVerilog that cover all of this topic. And you get to do actual exercises, and actually we do it in several lectures or whatever. But then we also add things like functional coverage and checkers and all of that. The universal verification methodology, UVM, is also discussed, as well as just a ton of other topics in here. So these are all places where you might want to try to extend here. So if you're in SOC design and verification, you should be learning these technologies. If you're in FPGAs, guess what? These are still useful technologies. Now you can also, look at VHDL and Verilog. They don't have the same facilities at this point, although I believe VHDL is moving a little bit that direction. But Verilog for sure is kind of a past tense at this point. It's SystemVerilog for all new designs, I would think. Okay, we have classes, of course, in embedded software and Python and deep learning. By the way, the concepts that we talk about in SystemVerilog are equally applicable to software design. That is to say, hitting designs with random data to test to see how robust the design is. And that might be, for example, against things like security issues or whatever, but also just to see how well your design holds up against the real world. This could be useful there as well. So stay tuned for other technologies coming in that particular area. So I want to thank you for your time and patience listening to this presentation. And I encourage you to review what we've covered. Maybe, there'll be some material sent to you after the webinar's over with. And, experiment. And then maybe I hope to see you in an upcoming course delivery. Thank you very much for your time.
Excellent. Our thanks to David for that presentation. Thank you all for attending. And once again, our thanks to Siemens for their promotional support of this event. As David mentioned, you can try out all the examples included in today's presentation using the Questa Advanced Simulator on EDA Playground. EDA Playground is a free-to-use online simulation environment provided by Doulos. However, if you've not used the site before, you will need to register, and access to some of the tools is subject to prior approval. If you are looking for more information from Siemens on Questa, please follow the link on screen and in the chat. We'd be very grateful for your feedback on this presentation, so please could you use the exit button on the GoToWebinar interface when you leave today and complete our survey. If you are looking for further related training, you might be interested in our comprehensive SystemVerilog training, structured to enable engineers to develop their skills to cover the full breadth of SystemVerilog features for both design and verification. Or for those with detailed knowledge of building class-based verification environments using SystemVerilog, our UVM adopter class training might well be of interest. Follow the links in the chat for more information and for the full course descriptions. All Doulos training can be delivered in person, live online, or as on-site team training. For an understanding of our full course portfolio, visit doulos.com/training. Feel free to use the last question of the exit survey to get in touch with us to discuss your specific training requirements. We're going to stay online briefly to answer any final questions you have about today's presentation. If you're unable to wait around, then we'll do our best to answer your question and include it in the Q&A log, which we'll send you along with a link to the recording of the webinar within the next few days. Many thanks again for attending today. Hope to see you again soon. Bye for now.